Today we're talking about how we can express acid strength as part of equilibrium. We want to do this so we can express how strong or weak an acid is quantitatively. Our success criteria is being able to convert between hydronium ion concentration and pH into percent ionization. So the big difference between strong acids and weak acids is the amount they ionize, and we often express this in terms of percentage. Weaker acids do not react 100%. A weaker acid can only ionize in water partially. Strong acids ionize completely. That's why the concentration of a strong acid and hydronium ions is the same, because they 100% ionize. But weak acids don't do that. So as a consequence of that, the properties of weak acids are lesser than the properties of strong acids. So weak acids are also weaker electrolytes than strong acids at the same concentration. They will react more slowly than a strong acid will. They will have more neutral pHs, so they trend towards a pH of 7. All of this is due simply to the partial ionization to hydronium ions of the weak acids. It's an incomplete reaction. We can say sometimes it's a qualitative reaction as opposed to a quantitative reaction. We can and will calculate numbers for it though, so often instead of saying it's qualitative, we say that it's an equilibrium instead of a quantitative reaction. So we are also going to bring in the constant of Ka. Now, K, as we've seen before, is equilibrium constant. Ka is simply the equilibrium constant of an acid. Weak acids will have Ka values that are lower than 1, and strong acids have Ka values that are much higher than 1. And you can actually see this on the very right-hand side of your acid-base table. The vast majority of weak acids will react less than 50%. We can calculate percent ionization values as well, but percent ionization has to be standardized at 1/10 of a mole per liter and at 25 degrees Celsius. And the reason for this is Le Chatelier's principle, because if you change the concentration, that actually changes where the balance of the equilibrium is. It may become more or less ionized. Same thing with the concentration, with the temperature. If you change the temperature, that's going to drive the reaction based on if it's exothermic or endothermic. So you have to do all of these percent ionizations under the same conditions in order to get comparable numbers to one another. However, if you do that, the higher the percent ionization, the stronger the acid is. For a hydronium ion, it's 100% ionization rate, so we can just say that the concentration is 100 over 100 times 1/10 of a mole per liter. If you had 97% ionization rate, you would say it's 97 over 100 times 1/10 of a mole per liter. So the 6 acids that 100% ionization rate applies to are the 6 at the top of our acid-base table: hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, and perchloric acid. For these acids, we can assume that the concentration is the same for the original acid and the hydronium ions. There are other strong acids out there. There are superacids that you might have heard of. We are not going to deal with those in grade 12. And in fact, quantifying superacids requires something different than the pH scale entirely, because pH doesn't really work well for them because they behave differently. The other thing I want to point out, because it's a very common mistake, is lots of chemists are very, very afraid of hydrofluoric acid. Hydrofluoric acid's not a strong acid though. It is one of the stronger weak acids, but it is actually a weak acid. The reason that hydrofluoric acid is something that chemists hate is actually because of the unique interactions between hydronium ions and the fluoride ion, which makes it particularly good at cutting through things that we tend to think as non-dissolvable, like glass. Any weaker acid than those strong acids, we can use a percent ionization. So the percentage is going to be equal to the hydronium ion concentration over the initial concentration of the weak acid times 100%. You could also rearrange that to be the number, the concentration of the hydronium ions is equal to the number of the percentage over 100 times the original concentration.